Hello and welcome. It's Luciano Lucas here. It's a pleasure to join you today and introduce Aivia 10.5. In the last several years, we've been building the platform that we call Aivia for the analysis of microscopy images. We've added functionality for 2, 3, and 4D image detection and tracking. We've added advanced workflows for spatial analysis and cellular analysis, as well as advanced recipes and pipelines for neuron detection. We've also leveraged the latest machine learning for both pixel classification as well as deep learning for image enhancement, segmentation, and classification. Last year, we introduced a new concept called Aivia That Learns. This is an AI that has learned from experts how to do analysis of an image using one of the recipes that we have. Last year, we talked about the 3D object analysis recipe. That was the one we automated. And we continue to work on this concept. And today we're introducing the latest iteration. Today is a very special day. Aivia 10.5 has an AI that has learned how to autonomously analyze neurons and reconstruct them in 3D. In this presentation, I'll have a chance to talk about the key concepts behind Aivia That Learns, also describe the data that we use for training, and share with you the results we can now achieve in terms of time savings as well as quality of segmentation. In addition to this, I'll briefly touch upon some other developments. We've added a lot of new functionality for our train and apply pipeline for deep learning models. We've updated TensorFlow, CUDA, and Python, and we've added extended support for Leica file formats. In this case, we added support for the Falcon modality. The brain continues to be much of an enigma. It controls all of our emotions, feelings, actions, and is responsible for so many diseases that we still don't understand completely. Governments across the world have set up large projects, this one in the US, the Brain Initiative, but there are similar projects in Japan, China, Australia, Israel, and in Europe that focus on understanding the structure at the individual level, at the regional level, and then the function of the brain. Researchers, however, are highly pressured to create scientific output with a relatively small amount of time for research activities. In a recent study published in 2021, it was shown that senior PIs and professors only have something like 6 hours a week to do research activities. And a more junior PI has only 10 hours. So it's a very, very little time. They have to be extremely efficient. And so the race is on to be very efficient. And we want to contribute to this efficiency gain by giving back some hours to the research community so that you can use those for critical thinking or for additional experiments or for whatever you decide is a good use of your time. The community has been rallying around the topic of neuron tracing, and you can see that as an increase in publications in the last several years. And we want to contribute to that acceleration because understanding the structure of neurons is going to help tremendously in understanding the structure and function of circuits and ultimately of the brain. Researchers spend tremendous amount of time creating beautiful images like the ones on the screen right now. Sample preparation, microscopy, and maintenance of that microscope. And even though the images are beautiful, this is not sufficient to really advance science, to advance the field. or to get published. It is necessary to extract segmented objects from this, like the ones on the screen right now. And from these, you can create some measurements, like count the number of neurons, know how many dendrites, what is the diameter, the length, the tortuosity, the branch angles, and so many more measurements. Then if you go one level up, you can start to create some insights related to relationships between neurons, populations of neurons, and neurons in different regions, how they behave, how they function, and also how they are affected by disease and how they may recover with certain treatments. And that's true insight. To get there, we need to analyze hundreds, sometimes many thousands of images, like the ones in the previous screen, in order to get to true insight. Researchers spend many hours putting image after image into your favorite software, analyzing it, and then doing it again and again and again and again. And each time you add an image to your favorite software, your software behaves as if it has never seen another image like that before. It's like it's the first microscopy image that has ever seen. In fact, you could put a picture of cats and it would behave just the same. You would still set thresholds, you would still apply filters, and the software would not know if it's a neuron or a cat in the image. What if we could do something different? What if the software could learn from these many hours of interaction? In fact, we estimated that globally, and this is an underestimate for sure, globally, more than 300 human work years are spent tracing neurons. In this one task, 304 work years from this community of neuroscientists. That's a large amount of very manual, repetitive work, which we think could be streamlined and automated for the benefit of science, for the benefit of human health and human life quality. So what we're proposing is to have a system in Aivia that can look at what the users are doing while they are converting a raw image into a segmentation map like this. Those behaviors are recorded, and together with the raw image that is processed, we create a fingerprint. And that image fingerprint, together with the parameters used, can be used to train an AI which learns the relationship between the image fingerprint and the parameters needed to create a good segmentation. We can then deploy that in Aivia and let the users simply apply that pre-trained AI, which can look at each image and determine what parameters to use for a good segmentation. Now, that's the concept, but it is a very, very challenging concept to realize. Just for scale, I try to estimate here how many possible parameter combinations there are for the recipes that we have, or the image analysis pipelines that we have for neuron analysis. And it's somewhere between 3.2 trillion for the simpler version of the recipe, all the way to more than 200 quadrillion possible parameter combinations. And that is a staggering number. So the scale of this challenge is tremendous. It's much more than looking at out in the sky, because there's only 10,000 visible stars in the night sky. So we're looking at a much larger scale than that. It's much more than the number of neurons in the brain. There's only 90 billion or so, 86 billion neurons. It's similar scale to the total number of cells that make up the human body at 37 trillion cells. And it's somewhere near the number of total synapses that exists in the human brain. 1 quadrillion. We're looking at possible parameter combinations of 3.2 all the way to trillion, all the way to 200 quadrillion. 200 quadrillion. That's 200 times more than the number of synapses in the brain. So that is a tremendous challenge, but we're up for it, and we think that it's worth investing our time to try and accelerate the rate of discovery in the space of neurosciences. So what we've done is create a dataset with 12 datasets. And these represent slightly different variations of neurons, different types of neurons, different types of imaging, modality, labeling, and density as well, as you can see. We took these images and we asked a group of experts to analyze them using Aivia, while keeping the system that tracks their user behavior on. This is, of course, an opt-in feature in Aivia, but we did that with internal users. This is the detailed view of the training strategy. So we take the usage data. As you can see, the raw telemetry data, what we call raw telemetry data is the usage data. So what parameters exactly are put into the image analysis recipe. That's one arm, and the other arm is the 3D image data set itself. We create 2D tiles from that. We do some data augmentation. We process that those 2D tiles through a pre-trained deep learning model, which creates a feature map, which we're also calling the image fingerprint. This feature map or image fingerprint is looks like a barcode, and you cannot come back from it to a real image. So it's anonymized at that point. That image fingerprint, together with the parameters, is what we use to train the predictive models for the right combination of parameters that Aivia can then use to populate the recipe autonomously. So we train a model that learns the relationship between the feature map, the image fingerprint, and the correct parameters for image segmentation. That is deployed into Aivia, and as a user, all you have to do is press the button that says automatic image determination, image analysis determination, and that will give you the right parameters for segmentation. So, moving into results. For those images that I showed a moment ago, it takes about 17 minutes per image on average for a human expert to get to the right result. For Aivia That Learns, it takes about 5 minutes to achieve a good result. But to get to the same level of quality as the human expert, it takes an additional 3 minutes. So Aivia That Learns plus indicates the autonomous result created by Aivia That Learns, plus a human expert doing some tweaks to the results. And that's additional 3 minutes. So in total, it takes 8 minutes. In all these bars, there are 4.4 minutes on average for processing the image. So to create the actual result, to apply the actual algorithm to the image and get the result. So if you subtract the 4.4 minutes from all the bars, you then have 12.57 minutes for the human expert to get to a result, 0.2 minutes for Aivia to create a first result autonomously, 100% autonomously, and 3.3 minutes if you do the fully autonomous plus some human expert tweaks. So it's another 3 minutes or so of human expert tweaks. So we are saving here over 70% of the human effort, of the human time. That's a tremendous amount of time that is saved, which can be deployed or redeployed for other tasks. This is so exciting, and we think that it's going to have a major impact to the rate of discovery in this space. So if we go back to the original or one of the earlier slides, we had estimated that globally more than 300 human work years are spent tracing neurons. We think that we can reduce that using Aivia to just 80 human work years tracing neurons. And that means there is more time for critical thinking, more time to rest, more time for leisure, more time for reading, whatever is the right answer for you. But there is less time of repetitive work that Aivia can do for you. So what does that look like within Aivia? Briefly show this video, then we'll go into the demo in a moment. You load an image and you can activate it either in the search bar on the top or inside the recipe itself. There is a little button that lets you turn on this functionality. Once Aivia finishes determining the parameters, it loads them directly into the recipe, and then you can just apply or start, and that creates the results for you. That's it. As simple as that. That's the simplest demo ever. Just press one button to predict, a second button to apply, and that is all. As I mentioned, this model was created using internal data, internal to Leica. So internal expert users were recruited to do this, but we have a system in place that can get data from anyone in the community that is willing to share their usage data. And you can turn those flags on when you install Aivia, or you can do it after it's installed. You can turn on and off whichever ones you choose. If you want to learn about what exactly we're doing with the data and what data we collect, you can look in this URL or search in Google for this string, and you'll get to this page to read all about it. With more people contributing, we can make Aivia better, and everyone in the community will be more efficient. An additional step or an additional part of this feedback loop has been also introduced. With every time a recipe is applied, if you have this option on, it will ask you how good was the analysis, how good are the results, and you can say good, okay, or bad. If you say good, nothing else is asked. If you say okay or bad, you're additionally asked if there's a problem with segmentation or with partitioning. Depending on what you say, Aivia will give a bigger or higher weight to your input or a lower weight to your input. So if you say it's good, it will give a higher weight to your input. If you say it's okay or bad, it gives a lower weight to the input. And that will be taken into consideration when we are updating the AI models for future versions of Aivia for the recipes that you're providing feedback on. So your contribution will make Aivia better and will help the whole community. Now we go into the demo. Okay, we are in Aivia 10.5. This is a pre-release version from the 12th of February. And before we introduce 10.5, and as I mentioned in the presentation just a moment ago, it would require a lot of human intervention, a lot of human time to get to the right parameters. And the procedure would be to set up all of these parameters to something that we think is reasonable, apply it to the image, check the results. Likely it wouldn't be perfect at the first go, so we would do it again and again and again, multiple times, adjusting the different parameters with slightly different combinations of parameters until we get to a good result. That would be the procedure. That is still the procedure for most cases. But in Aivia, you can now use the AI that I mentioned a moment ago, and you can activate it using the Neuron analysis tile right up here. That's what I will do. And you can see that CUDA will spike momentarily as it does the initial processing of this image and tries to predict the correct parameters from this image. So it's finishing up and already loaded the parameters in here. So these are the parameters that the pre-trained AI has selected. We can now apply them and wait for a moment until all the results are applied. Typically it takes, on average, it takes 4.5 minutes to apply. I don't know if this data set will be exactly 4.5 minutes, a little bit more, a little bit less, but we'll wait until the results are visible. All right, that has completed. And let's have a look if the results are good enough. Okay. It's pretty good. Yeah. So that would be considered good. Maybe not be perfect, but it's certainly good. And for this demonstration, it will be sufficient. So in this case, I didn't do any iteration. If I saw something that wasn't ideal, I could make a small edit to the parameters that were determined by the pre-trained AI and then apply again. Of course, I could also use a ROI instead of apply on the whole thing, so I don't have to wait for long. But now that I have all of the segmentation completed, I can start to explore this data set and look at some of the measurements, for example, in the spreadsheet. Look at the dendrite set that I just calculated, just detected. Can be visualized in the spreadsheet down here, or in the charts. Can start to explore, for example, mean diameter versus branch angle, and select any group. It is possible to select in complete cells, so this is a complete cell. You can see how it's distributed. Here's another. Here's another. And you can explore many other parameters. Branch count versus volume, for example. So these here are the ones with the highest branch counts. You can select that one, press Z, and go to it. Okay. So in this case, the pre-trained AI worked really well. It won't always work like this, but it's a pretty common that the result will be at least a very good preview, a very good initial result, and then very quickly can optimize using small tweaks in here. In addition to the ATL for neurons, we also have a few other features, and I'll describe them briefly now. Firstly, the new options for training and applying neural networks. You can now adjust the training hyperparameters. You can see several of the options visible in the screenshots here. Out of the box, it comes with the Arcan in 2D and 3D, as well as a UNet 2D and 3D. And you can set all your parameters here, from the learning rate to the block size, data augmentation type, and so on. You can also set the apply parameters. You can see the parameters that are available to set. It's possible to import, edit, and apply a neural network from outside of Aivia, as well as export one of the models that you work with within Aivia. We now have a new file format for the models in Aivia. They are Aivia DL, and this is a readable JSON based DL model file format, and it's backwards compatible with what we were using before, which was a HDF5E. We've also updated CUDA because we wanted to support the latest graphics boards. So we support NVIDIA RTX 30 series, as well as the NVIDIA Ampere based Quadros. Python is also updated. This improves performance, and it gives some additional features and tools for developers. We've also updated TensorFlow. This allows developers to use the latest neural network architectures. It has better performance as well as added flexibility. So in conclusion, this is a very special moment for all of us, and especially for the neuroscientists among us. Very exciting because we think we can save as much as 73.7, almost 74% of human time when analyzing neurons. It's a tremendous effort, and we hope it can be used to accelerate neurosciences, accelerate the rate of development, the discovery in this space, and ultimately improve human health. We've added highly flexible options for training and applying deep learning models for the more advanced users among us and developers. And we've added support for the latest GPUs so you can do things even faster. Finally, we've added additional support for Leica file formats, specifically for the Falcon imaging modality. And I'd like to conclude or get to a conclusion by thanking the whole team that has been involved in creating from concept all the way to launch, and in particular Hanyu, Hideki, Chishao, John, Casey, and Hoyen for their effort in this the most visible features in Aivia 10.5. Specifically ATL for neurons. Hoyen and Hanyu and Casey worked very hard on that. And for all the work on the deep learning pipeline, Hideki, Shishao, and John had large contributions. We now have a global sales and customer success team. You can see the team has expanded quite a bit. We have a position open in Boston. So if anybody wants to join, this is a great time to join us. That's how the team is distributed worldwide. Several representatives in Asia, Europe, and North America. There's always somebody nearby that is willing to help you and get the best out of Aivia. So reach out. Don't get stuck. If you are, do reach out. We will help you. Some final news and updates. Aivia is now available as a subscription, and we've made the switch to give you greater peace of mind. With a subscription, you not only invest relatively little at the beginning, but also you can always count on having full technical support as well as access to the latest software. You will never fall behind. You will always get support. Aivia 10.5 is available right now. You can go and try it. If you've never tried it, this is a great time to demo it. There is a position open in the Boston region. If you're in North America and want to join our sales and customer success team, this is a great time to do that. I'd like to finish by welcoming you to join the launch of Leica's MicroHub. It is a new imaging system, and you're very welcome to join it on the 3rd of March, not so long from now. With that, I'd like to thank you all for your interest in Aivia, in AI, and I hope you will try it and benefit from the tremendous advances that we are introducing with 10.5, which we hope will truly accelerate the rate of discovery in the field of neurosciences. Thank you for your attention.